So we will now talk about TK electrophilic substitution. Remember, is done. We will now be talking about the comparison, the relative comparison of hydrolysis of uh, chlorine derivative or chlorine related compounds. TK, there are plenty of chlorine related compounds. So we're going to talk about their hydrolysis. I said now, first thing is I'm going to make a table, and the table is what is hydrolysis basically? What hydrolysis is basically is that it's a reaction. Okay, this is what the overall reaction should look like. That there is something, some R, some rest of the molecule with a Cl, and you react it with water or with OH ions, and uh, the water or the OH ions will substitute the Cl with OH, and you will get ROH. That is what hydrolysis is, and the rest of the things that are going to be formed, the Cl minus one would get knocked out. So it's just a substitution reaction. What we are expecting is that the Cl in the compound, whatever the compound is, it's going to get substituted by OH. It's a reaction. It's going to be a reaction with water. Okay, that is hydrolysis with water, and this is the general reaction. So this here is the general reaction. Now, the first chlorine related compound that we will talk about, and let me make a table first. So I have a benzene, and that benzene has chlorine attached to it. Let me make the correct structure. So that benzene has chlorine attached to it. So here's my benzene, and here's a Cl. Okay, this is chlorobenzene. This is the first chlorine related compound that we will do when we are comparing it. So that's number one. Number two is a normal. So this is chlorobenzene. Let me write the name. So benzene plus chlorine. We're going to study the hydrolysis of this compound. The next one is a halogenoalkane. So it's basically a carbon chain. So you have, let's say you have a carbon chain, and that carbon chain has Cl attached to it. Now you've already studied the hydrolysis of halogenoalkanes. This is a halogenoalkane. And the last one that we're going to do when we're comparing it, that's acylchloride. That is a carbon chain, let's say CH3, with this thing is an acyl group. It's C double bond O and Cl. So that is what an acylchloride is. Okay, this is the comparison that has to be done. The middle, and they've been written in the right order. What's basically happening is that the speed of hydrolysis increases. It becomes easier to hydrolyze. Your acyl chlorides are very fast. Their hydrolysis is very fast. Chlorobenzene have almost no hydrolysis. So we're going to write that as well. This one, okay, we're going to individually study them one by one. No hydrolysis, no reaction with water or with OH. Halogenoalkanes, which you have studied earlier, and we're going to do that again. They hydrolyze slowly. And you need NaOH aqueous and reflux. plus reflux is needed. And the third one has vigorous hydrolysis. Okay, and we're going to study why it has vigorous hydrolysis. So the third one uh, reacts vigorously even with cold water. And even with cold water. So vigorous hydrolysis takes place for the third one. So that's basically your table that you have to know. The three chlorine-related compounds: chlorobenzenes, halogenoalkanes, and acylchlorides. And not only do you need to know which one is going to react with water, it's just that the Cl is getting replaced in all of them by OH groups. So which one is going to react very violently? Acylchlorides would have a vigorous reaction, whereas Cl is going to have a very slow reaction. Uh, so we're going to study each reaction one by one, and we need to know why this reaction is slow or non-existent, and why this reaction is very fast. So I'm going to start with the first one, chlorobenzene. So let's start talking about hydrolysis of chlorobenzene. Basically, there is no hydrolysis of chlorobenzene. Okay, so there is no hydrolysis of chlorobenzene. So what's the reason for that? The reason for that is that there is a benzene ring, and the benzene ring has pi electron clouds, and the Cl is attached to such a benzene. So there is a Cl, and this over here is your benzene ring. So why does OH not react with it? Why does OH not substitute it? So if you introduce OH minus 1, what's going to happen is that Cl has its lone pairs. So there are plenty of lone pairs. Uh, Cl over here has plenty of lone pairs. There are three lone pairs on Cl. And as we have previously discussed, that the lone pairs and the electron cloud, they start overlapping. And the end result is they're going to be, I mean, the electrons over here. You can remember Cl is 3,5 directing. So the electron density over here is going to increase this side. And not only would it increase, it would start overlapping with the electron density with the lone pairs of Cl. So the end result is there's going to be a lot of electrons over here. I mean, there's a pi electron cloud plus, in addition to that, the lone pairs on Cl, which are plenty of lone pairs, they also start overlapping, and as a result, there are lots and lots of electrons over here. Okay, is this clear, Aisha? Sara, is this clear?
Yes, sir.
And so,
Yes, sir.
so the simple answer is, if there are lots of electrons over here, the negative OH ion is going to get repelled because it's negatively charged, and this is also negatively charged. So there's going to be repulsion. So this one over here is going to get it's going to get repelled. So in your paper, if you're asked why there is no hydrolysis, why doesn't it react with OH? Why doesn't the Cl get substituted? What you're going to write is that the lone pairs. This is the explanation that you're going to give. The lone pairs on Cl overlap with benzene's pi electron cloud, which increases the strength of the CCl bond because now it has more electrons. The bond has more electrons. If the bond has more electrons, the Cl in the carbon bond has more electrons, then it's a stronger bond. So which increases strength of the carbon and chlorine bond, and the OH nucleophile gets repelled. So the OH nucleophile is going to get repelled. OH, or you can also call it water. Okay? Any water molecule, the lone pairs on oxygen are going to get repelled. Okay? So it's either OH or and why do you call it a nucleophile? Nucleophiles are negative ions because they are attracted to positive charge. There is no positive charge over here. Okay? Achha, next one. Is this clear, Sarah? Aisha, is this clear? Take a simple explanation.
Yes, sir.
Yes, sir.
Achha, now next one. Let's talk about hydrolysis of halogenoalkanes, and you've already studied halogenoalkanes in AS. Okay, so let's talk about hydrolysis of halogenoalkanes. Okay, this was Sn1 and Sn2 mechanisms, which you've done in AS, and which can be asked again. TK usually do because they always do a comparison with chlorobenzene, just like electrophilic addition and electrophilic substitution. They are often compared. So hydrolysis of halogenoalkanes, you have. I'm going to first write the reaction. What's going to happen is, if there is a Cl attached, the conditions are that you're going to add NaOH aqueous and reflux. So the reaction is basically happening with OH ions, and it could be KOH as well. So the reaction is basically happening with OH ions, and the OH ions. So the reaction is happening with OH ions, and the OH ions are going to come in, and they're going to substitute. They would substitute the Cl with OH, and Cl minus 1 would be produced as a result. So that's a simple reaction. So why do you have Sn1 and Sn2 mechanism? So Sn2 mechanism happens with it happens with primary halogenoalkanes. So primary halogenoalkanes, that's Sn2. And what happens in primary halogenoalkanes is you have a carbon chain. So what's a primary halogenoalkane? A primary halogenoalkane is that the carbon would be bonded to two hydrogens and there's only going to be one carbon chain. So on one side there is a carbon chain. That's a primary halogenoalkane. The CCl bond is polar. The carbon over here is positive and the Cl is partial negative, and there are two electrons in this bond. The next part is that the nucleophile, which is OH, and this is Sn stands for nucleophilic substitution. So the nucleophile, which is OH minus 1 in this case, it's going to attack the carbon positive. It's going to get attracted to the carbon positive, and when it gets attracted to the carbon positive, as this negative ion approaches, it comes closer to it. The electrons over here in this bond are going to get repelled. So this is what's happening. And remember that the OH is going to attack from the other side because this side is negative already. So the negative ion would not be approaching from this side. It would be attacking from the opposite side, the positive carbon, which this bond is already polar because there is Cl attached. So the OH negative is going to get attracted to the positive carbon atom and the Cl electrons are going to get repelled. So the next step of the mechanism is that you're going to have R. I mean, the molecule, the rest of the molecule remains pretty much the same. So you're going to have R, C, and two hydrogens. And the Cl bond would slowly break away. It's going to slowly take the electrons, and the OH bond, the OH is approaching from this side. The OH would slowly form a bond. So in the middle, there's going to be a step where the carbon atom, for a very momentary instant, it's a transition state. So for a very small amount of time, that carbon atom would be bonded to five atoms, and a negative ion would be formed. This is known as a transition state. It's different from an intermediate because this state is highly unstable. It's not going to last for a very long time, and eventually the Cl would break away, and the OH would take its place. So that's your final step. The OH would replace. So the final step is that your molecule with its hydrogens, the OH would eventually take Cl's position, and the Cl minus one has eventually broken off. Okay, so this is the final step. Okay, is this clear, Sarah? Aisha, is this clear?
Yes, sir.
Yes, sir.
Acha, and this is a one-step reaction. Okay, these are not two steps. It's a one-step reaction. And the middle part is just a transition state. It just shows a picture of a small glimpse. It's I mean you had this thing and then you eventually had this thing. So just one step is happening. The middle part is just a very tiny instant in which this thing would exist. The OH would be coming in, the Cl would be breaking off. So this is what's happening here. So that is primary halogenoalkanes. The other one is the other mechanism is Sn1. Okay, when do you have Sn1 reaction mechanism? Okay, Sn1 is for tertiary halogenoalkanes. Now, when you have a tertiary halogenoalkane, what happens is that in a tertiary halogenoalkane, the carbon is surrounded by large groups. So on all sides, there are carbon chains. So there is an alkyl chain, another alkyl chain on this side, and another alkyl chain on the other side, and it's bonded to Cl. So you have a partial positive charge on the carbon atom and a partial negative charge on the Cl atom. Now, in this case, what the real problem is that there is no room for OH minus 1 to approach or attack the positive carbon atom. Why? Because they're very large groups attached to it. So there's a huge carbon chain over here and a huge carbon chain over here, another huge carbon chain over here. So it's very hard for the OH minus 1 to actually come and attack because it's going to be blocked from this side, okay, because of the larger groups. In the previous case, the OH minus 1 could attack this carbon atom directly. Why? Because it was surrounded by hydrogens. So hydrogen is just one proton. So these sides were open and the OH minus 1 could easily sneak in. But now that's a problem. So the OH minus 1 cannot really attack. So so that OH minus 1 is not involved in the first step. What eventually happens in the first step is that during collisions, you're going to wait because the OH minus 1 it cannot do anything. So in the first step, you have to wait. The carbon Cl bond is already polar, and during collisions, there are chances that it might break away, which is why you're using reflux. Okay, the conditions for this reaction was the NaOH aqueous and reflux. Reflux provides enough heat that the CCl bond breaks off on its own. But this is a slow step. It's going to take time. So that's the step number one is your slow step. And that results in the formation of a carbocation with three carbon chains. And this carbocation is very stable because the Cl minus 1 takes away its electrons. So it's a highly stable carbocation. Remember, carbocations with three carbon chains are very stable, or you can call it a tertiary carbocation. Alkyl chains have electron donating effect, have electron donating effect. What that basically means is that all the alkyl chains, carbon chains, whenever you have carbon chains, they have lots of electrons. Okay? Unlike hydrogens, if the carbon is surrounded by hydrogen, hydrogen doesn't really have electrons. It only has one electron. But a carbon chain has lots and lots of electrons. Like carbon itself has six electrons compared to hydrogen. So if there's a positive charge in the center of the carbon chains, the positive charge is going to be smaller in size. It's going to have a lower charge density. It's going to have a very low charge density because it's going to pull the electrons from all the sides, from all the carbon chains, and the positive charge would be neutralized to some extent. So that is what electron donating effect would do. That the charge density on the carbocation would be lesser as it is surrounded by large chains. ठीक है आयशा सारा is this clear?
Yes.
Yes, sir.
Acha, so Acha, what that allows for is that the Cl minus one would be able to break away. Because if the positive charge was actually strong, I mean, if this positive charge was really large, then the it would have been very difficult for the Cl minus one to break away, and it would remain connected. So because the positive charge, if the Cl breaks away, is kind of tiny, it's very small. It gets smaller because of the electron donating effect of the neighboring carbon chains. That is the reason why the carbocation is a stable. It's a stable intermediate, which means that it allows the Cl minus one to break away instead of attracting it, and that gives OH minus one room so that it can come in and it can join that carbocation. So if the OH ion concentration is sufficiently high enough, because you're adding NOH, if you add a lot of NOH, there would be lots of OH ions. So the chances of OH ions connecting with the carbon would be very, very high. And that results in a substitution. And finally, your product is going to be formed. And the product would be that the Cl has gotten substituted by OH. So the carbocation joins with the OH and the Cl minus one has broken away. Okay, so that's your mechanism of hydrolysis of halogenoalkanes. Okay, Akib, can you hear me?
Yes.
Okay, so I'm just going to repeat what we were doing. Okay, we're basically discussing we're basically discussing hydrolysis of chlorine related compounds, and there are three chlorine related compounds that we're going to study. One is chlorobenzene, okay, a benzene ring attached with chlorine. The other one is a halogenoalkane, which you have already studied in AS. And this is an acylchloride, which is C double bond O NCl. And hydrolysis is the reaction with OH or water. And for the first one, I said there was not going to be any hydrolysis. For the last one, I said that the hydrolysis would be very fast. And the middle one, which we have already studied, it has moderate reaction. It slowly hydrolyzes if you have NaOH aqueous and you reflux it. So the first one, I'm just quickly recapping the first one. Why is there no hydrolysis? Because the benzene electron cloud has lots and lots of electrons on it, and the Cl has lone pairs. Eventually, the electrons kind of start overlapping because the lone pairs over here, there are lots of spare orbitals which are completely full over here, and the benzene electron cloud, they start overlapping, and you get lots of electrons over here. And electrons, whenever there are more electrons, a nucleophile with a negative charge is going to get repelled because both of them are negative, which is why you don't have a reaction. But why do you have a reaction in halogenoalkanes? In halogenoalkanes, you just have one carbon that's bonded to Cl, and the Cl is partial negative and the carbon is positive. So in a primary halogenoalkane, the mechanism is that the OH nucleophile, okay, this over here is a nucleophile. Let me also add that. So the OH minus one nucleophile, it's going to get attracted very strongly to the carbon positive. And because the carbon positive is surrounded by small atoms, so it can easily sneak in and attach to it. So the OH would be attaching to the carbon atom. At the same time, because of the negative charge over here, the Cl would be getting repelled because it's also negative. So the Cl kind of breaks away and the OH goes and bonds with the carbon atom. And in a tertiary halogenoalkane, the carbon was again bonded to Cl. It was a polar bond, but it was surrounded by large groups. So the first thing is the OH minus one cannot really attack it because of the surrounding larger groups. They won't allow it to reach the central carbon, positive carbon atom. And so the Cl minus one would break away. And I also said why this was a stable intermediate, because the positive charge would not be very strong because it's going to pull electrons from all the sides, from all the carbon chains which have electron donating effect. And if you have, so the positive charge would be smaller. That allows the Cl minus 1 to break away. And if OH ion concentration is sufficiently high enough, it goes and connects with the carbon atom, forming an alcohol. Okay. So, Akib, is this clear?
Yes, sir.
Sara, Aisha, is this, everything clear? Quick question to you.
No, sir. It's clear.
Acha, the last one, that's an acyl chloride. Okay. So, acyl chlorides have vigorous. Remember, halogenoalkane, it needs NaOH aqueous and reflux. But in acyl chloride, they have vigorous reaction with cold water. And you, in A2, you have to know the mechanism as well. Have vigorous reaction with cold water. So no catalyst required, no OH ions required. The reaction would simply happen with cold water. And a vigorous reaction would happen. So what's up with acyl chloride that the reaction is very, very vigorous? So you have, this is your typical acyl chloride. It's going to react with water. No conditions, no nothing required. A vigorous reaction would happen. And you're going to get R, C, double bond O, and the Cl is going to get replaced, knocked out by OH ions. And HCl would be produced. And this HCl would appear as misty white fumes. So as soon as you add an acyl chloride to water, you start seeing a lot of fumes forming. So this is what's happening. Uh, and you have vigorous reaction. And let me add cold water as well. Like with warm water, it's obvious it's going to happen, but it also happens with cold water. So why is the reaction very, very fast? And the mechanism of the reaction. Now, the mechanism, what's the name of the mechanism? The name of the mechanism is, this is called nucleophilic addition elimination. So now that's the name of the mechanism. And here you have an acyl chloride, RC, double bond O and OH, not OHCl. So it's RC double bond O and Cl. As the first thing, the carbon has a very strong positive charge. The reason being because it's attached to two electronegative elements, right? So there's oxygen that's trying to pull electrons, and there's a Cl as well that's trying to pull the electrons. So the positive charge density on carbon is very high. So on C in RCOCl is very high. Okay, so this would be asked as well, is very high. Why is it high? Because it is bonded to two electronegative elements. Two electronegative as it's bonded to two electronegative elements, which is why if there's a water molecule around, the water molecule is going to be strongly attracted to it. So let's say there's a water molecule, and the water molecule has these lone pairs which have a negative charge. So the water molecule is going to be strongly attracted to the carbon which is positive. So that's the first step. Okay, there's going to be a very strong, vigorous reaction because strong positive carbon atom, oxygen is very electronegative, Cl is very electronegative, so highly polar carbon atom, and it attracts the lone pairs from water molecules. Okay, is this clear, Aisha, Sara, Akib? Is this clear?
Yes, sir.
Achha, and as the water molecule approaches, the electrons in the double bond, especially the pi electron cloud, it kind of starts getting repelled. Okay, so there's this pi electron cloud on this over here, and the pi electron cloud gets repelled. So that's the first step. And what's going to be formed is this thing. So the intermediate is the first part is called addition. So addition is happening. Water is going to get added. So you have R and you have C and you had a double bond O and a Cl, right? Now what's going to happen is that the water molecule would come in and it would bond, and its lone pairs are going to bond with, and there's only going to be one lone pair left, right? So water is basically losing electrons because its electrons have traveled and have bonded to carbon. So water gets a positive charge. So there's this positive charge that has built up on this water molecule. Reason being because it lost its lone pair. Lone pair got attracted to the carbon very strongly. And at the same time, this double bond over here, its electrons they were getting repelled, right? Because of water's lone pair. So there's only going to be one bond left over here, and this oxygen will have a -1 charge now because the double bonded electrons over here, they have been repelled and they're now with oxygen over here. So oxygen has these extra electrons now at the top. Okay, is this clear to everyone? Akib, Aisha, Sara, is this clear?
Yes, sir.
Yes, sir.
I said, then the next part. What happens after this? What happens after this is uh, these electrons over here. What happens after this is that this negative charge over here has accumulated, but the bond hasn't broken, so the oxygen is still there. Eventually, what happens is that the double bond gets reformed. Okay, so this is an intermediate. The electrons come back, and the double bonds they kind of get they're formed again. I mean, the double bond over here that was broken that forms again. But when these electrons come back, the electrons from the Cl get repelled, and the Cl breaks off. Okay, so that's your elimination stage. So in the next step, elimination is happening. So you had addition, now elimination has started taking place. Okay, so remember the pi electron cloud. Okay, they were easier to repel because they're further away from the nucleus. So initially the pi electron cloud, the double bond pi electron cloud, it got repelled, and all the electrons accumulated over here, but the bond was still there. So eventually the electrons are going to come back. They're going to try and come back, reform the double bond, and Cl would eventually take its electrons and leave. So the next step is, okay, I'm going to draw the molecule now. So the next step is that the double bond with oxygen has reformed. Cl -1 has taken its electrons and it has left. Okay, that's gone. And you have at the bottom you have an O that's still attached. And the O has a positive charge. Why does it have a positive charge? Because वो शुरू में ना it had lost its electron to carbon atom, so the O is still positively charged. Finally, the the last step is another elimination would happen that the positive oxygen needs electrons. It needs, I mean, there are two lone pairs. It needs its lone pair back again. The final end में वो क्या करेगा कि वो it's going to take hydrogen's electrons. ठीक है, just one second, let me draw the hydrogen properly. So there's a bond over here, and the final step is that these electrons go back to oxygen. इनको थोड़ा सा साइड पे कर लेते हैं. ठीक है, so these electrons they go back to oxygen and the lone pair is reformed. तो इससे आगे चलते हैं कि so it's going to become RC double bond O and the bottom part would be OH. ठीक है, and the O would have both its lone pairs now because the H left its electron. वो H किधर गया? It combined with the Cl and ended up forming HCl gas. That's where you're getting the fumes. So I'm going to repeat the mechanism. ठीक है, so it's probably one of the longest mechanisms that you have studied. And that's your addition elimination mechanism for hydrolysis of acyl chloride. So you started off with an acyl chloride. The carbon had a very strong positive charge. The water lone pairs they got attracted, and the pi electron cloud in oxygen, this double bond, it got repelled, and you got a negative charge over here. The water molecule got attracted, and because it was using its lone pair, it became positively charged because carbon was taking away electrons from it. And in the next step, the repelled electrons in the pi electron cloud they came back, they formed the double bond back again, and as a result, because those electrons are coming back, these electrons got repelled and the Cl-1 broke away. And the final step is वो starts in this oxygen over here was electron deprived because its electrons got attracted to the carbon atom, so it needed electrons, so it pulled the electrons from hydrogen, and the H+1 left and bonded with Cl-1 to form HCl. It ended up forming HCl, and oxygen got its two lone pairs back again, so it was neutral again, and that's how carboxylic acid is going to be formed in this reaction. ठीक है? Is this clear, Sara, Aisha, Akib? Is this all clear?
Yes, sir.
Akib, is this clear?
Yes, sir.
I said so. Three things. Okay, you have. I mean, all of them. They would be. You're going to get questions, big questions on this comparatively related to hydrolysis. Make sure you're able to identify whether it's a chlorobenzene. A chlorobenzene is when it's chlorine is attached directly to benzene. Acylchloride is when it's attached to acetyl bond O, and halogenoalkane is when it's attached to a carbon chain. This is Sn1 Sn2 mechanism. This is addition elimination mechanism, and this has no reaction. Okay, so we've done all three. Okay, all three are going to come in comparison. So if do you have any questions about this? नहीं है तो we'll continue in the next class then. ठीक है?
Right, sir.
चलो. Okay then.
Allah Hafiz.
Take care. Allah Hafiz.